Hi, Dean.
There's a ding. There's a ding. Hey, how you doing?
Good and you. Sorry, I'm driving, so it was about fiddly to get it off mute. But
No, that's fine. One quick question for you before I run through my preamble stuff. Are you getting some snow out there or what?
it's cloudy and it looks like it's gonna snow, but nothing yet. Nothing yet.
And that's
It's
just
zero
right after.
degrees, so it's like, but nothing. I'm on my way to Olds.
Yeah,
I can't see anything while I'm midway there, but nothing. No snow. It's overcasted
yeah.
quite heavily, so we'll see.
Oh,
Hopefully.
yeah. Okay. Cool. Thanks for the quick update. So what I'm going to do is we've got a great presenter today, and I don't know if Dean, your counterpart, Mahi's able to hop on or not. But what I'm going to do before that is just there's a couple of a few little slides of note that caught my eye that I wanted just to touch on real briefly. So I'm going to start with that. But again, welcome everyone that's able to attend the March 27th Coffee Talk. And what this is about, lots of a chatter about tariffs and all that stuff, right? And what I wanted to do is here's what the Chinese have to deal with for imports. And so over on, this is what there was, and I'll just pick one, we'll call it glufosinate down in the middle. It didn't used to have any surcharge from China. Then we had a base tariff that was on there. And now they've added a 20% onto that. So their total import into the US is 23.7%. And then that has a range, 240, like the phenoxy's up at 34. This one's at 51. This one's at 51, and so on. And a lot of that is relating to they have some domestic production. So they don't, maybe they're just kind of discourage some of the imports. But the bottom line is this goes to the American farmers' P&L. Thus far, Canada's been insulated from this. And then there are some US-based corporations where this is impacting them, i.e. Bayer and BASF, where the US production's, there for them being able to, we don't know what's going to happen with them bringing across the lines, but for them to bring in their product from China, their actives and stuff, that's a factor for those guys. So just a quick thing on that. And have a little bit on some fertilizer because what Dean is going to be talking about relates to fertilizer and fertilizer usage and stuff like that. So he's going to be presenting a little bit of innovation on what they're working on and how the plants work and all this stuff. But the bottom line, I had showed the slide earlier. And if we take a look at, here's February in 2020, we were at 462 a metric ton, and then 623, then 1245, then 797, then 725, and now we're up at 826 for this month. And what that is going to mean is where is it all, like who all's the producers and what's coming in and all the rest of it. And as I had indicated, historically the Chinese had exported 5 to 5.5 million tons of urea, and this year they're at or 24, they did like 250,000 tons. So they're like 5 million tons less exports of what their kind of historical was. So where does that stuff come from, and does it matter? Does it really matter to where we're going? Well, it kind of matters because right now, instead of last year there being 90 million acres of corn, the forecast, the latest one as of a couple of days ago by this outfit, Ag Market, they're at north of 95 million acres, and beans taking the hit. The reason for that is the corn is substantially more profitable. They've got the ethanol system in place and all that, and there's some internal struggles that they're sorting out with that 45Z program with those guys. Wheat's pretty static, but it's going to mean, based on the quick and dirty I checked on, corn chews up about 200 pounds of actual N, and any agronomist can critique me on that. That's just what I found, which is 400 of aggregate or gross. And so it's about 1 million tons of production that will have to fill the void from a year ago and whatnot. So what does that mean? Is nitrogen going to go down in price? I don't think so, like it's got to come from somewhere. And then we do have the latest related to the Canadian stats. I was talking with Ken Edwards a little earlier on the call relating to the Canadian stuff, and with his growers that he does crop planning with, there's still some flex acres. People are still wondering about the canola acres and that. At this time, they're forecasting a bit of a decrease on that stuff. And wheat being one of the worst paying crops. This is a bounce up, but this is a little bit like this was like earlier on in the year. But perhaps oats displacing that as one thing. And we'll see what happens where the peas went up quite a bit. But again, we've got the Chinese throwing their tariff on stuff. So there's a bit of ambiguity at this time as to what to expect. But nitrogen use up in the US substantially compared to last year. And we've still got some wild cards in Canada. And we'll see what happens with that. But ultimately, it works out to what's going to be profitable for guys in factory and rotation and chemistry rotations and all the rest of it. So that was a bit of a tee up for you, Dean, as to what we're going to learn about today. I've had the pleasure of knowing Dean for probably 4 or 5 years now. I'll save you the pain point of your background, Dean. But Dean is in the Wilkie, Saskatchewan area. He was one of the founders of Great Northern Growers, with him and his brother in that. And then FBN purchased that business from the Skinner brothers. And then over that period and then during the time that Dean worked within FBN, he vetted an awful lot of the innovative products coming down the pike, particularly in the biological front. That's a real passion of his. And he's working with Mahendran, and I'm not sure if Mahendran will be on the call today, but they have some really cool things that they're working on. But what we're going to talk about today is, to start with, is Dean's take on how the plant works, how the soil works, and their take on where they can maybe make a difference and share some insights. So with that, Dean, welcome, buddy. Hopefully I did you some justice, and if I missed anything important, chip in, buddy.
Well, great. Thanks, Dean. Thanks very much. I recognize a lot of names on here, so I think that with some of our past background together, certainly a lot of these guys are aware of. But yeah, I started out on a farm, as Dean says, went through the School of Ag, got a bunch of scholarships to continue, so went into the degree and did a lot of agriculture, ag business, and also microbiology, so that I didn't use the microbiology right away, but as Dean mentioned, got into it as we started with our own company. One of the things that struck me when I took ag economics at U of S is the professor saying that the chemical companies don't charge based on their cost. They charge on what they figure how much we can figure to pay on it. And that kind of annoyed me and was my fuel to bringing in generics to try to bring down different chemistry prices like glyphosate and that. So through the years, as we got more and more chemicals on the book and had to pay more and more data comps, some of them were up to $15 million, we thought we should sell to a bigger company because we didn't want to take all that risk. I agreed to stay on as long as I got to work on the biological side, and predominantly they had me working in the US, but I've always been from here, so I've always been interested in this. I'm going to talk a little bit today. I think it's really important for growers to understand a bit of how the plant works so that you can form your own strategies and understand, some of the things we want to accomplish. So if you want to jump to the next slide, Dean, we'll get into the presentation. And what it really comes down to, what is soil health besides a very overused term that, is somewhat maligned, but to me, dead things don't have health. So for a simplicity to that, it's the living part of the soil. And when we look at the soil, what does it look like? Well, it's kind of like a dark brown to black cottage cheese. When we shovel into it, would indicate a nice healthy soil. And when we think about soil, because we don't see what's going on down there, I want to emphasize that the two main components, this would be in a healthy soil, would be bacteria and fungus, and we can have about 4,000 pounds of each. So if we think about that, that's 8,000 pounds an acre. That would almost be like a little over 6 cows an acre. So if you wanted to say, 1,000 cows on a quarter section, if you visualize that, you'd be like, wow, that's a big herd. And we don't see what's below the ground, but potentially in a healthy soil, that's the amount of life in the soil. And if you think about, geez, what's the feed bill on that? They do need feed, water, and air to survive and to create a healthy soil. And I want to talk about, how we practice ag today, some of these conditions are lacking, and this is impeding the soil health and some of the benefits we could be deriving from that. Next slide, Dean. One of the symptoms of poor soil structure is something like this. A good structured soil should easily be able to infiltrate 2 inches of water in about 15 minutes. And when we get this water pooling on the surface, of course, if you have a hill, it's going to run down into the low spot. That's going to flood out the low spot. So sometimes those low spots, some years are our best yielding, sometimes we get nothing. But I guess my point in that is we want to be able to capture that water where it falls. So if it falls on the hill, we don't want it flooding the low spot. We want it, benefiting where that falls. And when we get good structure, that's something that will come along with it. Next slide. I use this is obviously not my slide, but it's an illustration probably a lot of guys have seen, breaking or these different things, how, we have a lot, what's going on there that in this field, there's an extreme drought. This farmer was using, a conventional farming system. Why is the regular field that's been farmed a long time burnt to nothing, yet that strip down the side looks very good? When I was in school, they would explain that to us. Well, there must be some nitrogen in that, but obviously we can put as much nitrogen down on that burnt out part of the field, and it's just going to be a waste of money. So it triggered my interest is, why is that going on? And beyond that is, can we get our regular field, the burnout part, to have the resilience that this strip does? And that is part of what, can we get the plant to actually, like a cover crop, start building our soils back so that, in these dry conditions, we could actually have a lush looking crop like this. Yeah, that would be a fence line, Brett. Absolutely. Next slide, Dean. So what I wanted to get into is just, we think about NPK as the major nutrients of the plant. But if we take out the water, which is 80% of the plant, most of a plant is actually, as you can see in the lower one, carbon is about 47%, oxygen's about 43%. Then hydrogen is about 4%. So right there, we've got about 94% of the plant is actually made up of those ingredients, the carbon dioxide, of course, creating, and water forming those sugars. So most of our deficiencies actually in some of these soils are actually carbon, oxygen, or of course hydrogen. A lot of people don't think of hydrogen, but when you talk pH, it's potential hydrogen, or the power of hydrogen is what it stands for. And it has a very strong implication on how nutrients become available. And certainly as we get very acidic or very alkaline, it's going to cause a lot of challenges for the crop. Next slide. So I like to think of these things as tools, as chemicals, fertilizer, any sort of product, as a tool that the farmer can use. And in this case, we'll get into a little bit why we're trying to give the plant some tools to work with some of the modern science that's coming out. And I want to start to think of this as a little bit like, ourselves, if we come out of school or high school or college as athletes, say, and we sit on the couch and drink pizza or eat pizza, drink beer and pop and eat chips for snacks. After about a decade, if we go back and try and be these athletes, we're probably going to have a bad experience with that and find out. And the soil's very much the same. If we haven't fed that biology, and I'll get in a little bit why, for a very long time. So it does take a bit of strategy to start building that health back with our cash crops. And I want to talk to you some of the science that allows us to do that. So, it's kind of like rebuilding an ecosystem and some of the benefits we can derive from that. Dean? Slide. We had a miscommunication today, as Dean mentioned, about Mahedrin being on. So I didn't put a lot in on this topic. Basically, there's a lot of organisms, mycorrhizal fungi, is kind of considered the king or queen. I'm going to talk a bit about that in this slide. Trichoderma is very used in the horticulture industry. It's usually about $50 to $70 an acre. It's not been very available in broadacre. That is also in this product. And then a bunch of just very proven microbes that are efficient at breaking out a lot of different minerals and stimulating root growth and that type of thing. But we'll jump to the next slide, Dean. So this picture, that little white spot is a mycorrhizal spore. And what I wanted to demonstrate with this is as it germinates, because it's in this granule that we have created, it will grow into the plant root beside it. And it grows into sort of the intercellular space and it occupies that. And that's one of the ways it prevents disease, but it also allows it to get carbon from the plant, and it'll trade things like water and phosphorus and break out other nutrients within the soil. So it does enact some protection and nutrient transfer into the plant. Next slide, Dean. Slide, Dean. Yeah, thanks. So if you look at this is the big cylinder in the middle is the root hair. And is a root hair. So this is very blown up, very microscopic. This wouldn't be visible to the naked eye, but all those strands coming off of there is mycorrhizal fungi. And I heard it said once that, the roots are almost like our primary highway system. And mycorrhizal fungi is like the grid roads and back roads that get us into every field. As you can see, the surface area and the ability of the mycorrhizal fungi to essentially it can grow meters from the plant, pull in water, pull in nutrients from all over the field. It's really an amazing organism, but it's sensitive to some of the practices that we do with regular farming. So we'll talk a little bit about how we can mitigate that, because I always say to Dean, I don't want to promote guys to use something like this and spend your dollars on it if we're just going to kill it with what we're doing. It's a waste of money. So, it always comes down to, thinking about our operation, what we want to accomplish, and whether this tool is suitable for us. So next slide, Dean. What happens with the plant is plants are actually very capable. And if we look at the picture here, you see another root hair. All that white substance, that milky substance is actually, this is a real photo, is actually sugars that the plant is feeding to the microbes. And this process is very important to building soil health, because as you can imagine, a healthy plant will put up to 60% of its energy to the microbes around it. And these are actually designed to feed a specific microbe. So if a plant, say, needs phos or iron or potassium, it can pick what bacteria that does that or fungus that will do that and feed it specifically. And what that does is allow then, as I'm going to show, how this will bring those nutrients from what we would consider unavailable in the science. So it's not going to show up as nitrate or phosphate on a soil test. It's going to be in the rock mineral form, but we can bring that into the plant. Next slide, Dean. So when we dig our roots up, if you see nice clean white roots, they look nice, but that's actually a strong indication you don't have great soil health. When you pump all those sugars out around, you're going to get what is called a rhizosheath. So it's like this big area around the root that is like premium space for the microbes. They can actually modulate the pH in there so that the nutrients become very available. And if you want to picture a plant, you know, you see what's above ground, right? And let's just say that's 20% of the plant. If we get good exudation, normally that's going to actually be over half of the plant's sugar. And I'm going to talk a little bit more about that. But when you get these big rhizosheaths underneath, that's what actually starts to build the structure. If you get a root system as large as the top, and then you get, you know, actually 3 times more carbon feeding the biology, you start to grow this massive structure. And this is when we start to actually see the soil health and can start to build that soil up. Next slide. So the next thing I want to talk to, this is new science. If anyone's interested, you'd find it under rhizophagy cycle. Don't get confused. The rhizo just means root. It's kind of the Latin, and phagy means eat. But what it has demonstrated is that plants can eat microbes. When we went to university, they taught us this simple ion theory that only the ions were absorbed. But the interesting thing about a microbe, as I'm going to show you in the next slide, is that it does contain the energy and all these other things. So the plant can actually farm microbes, giving them sugar, and they break the minerals out of the soil, and they create the, you know, turn the nitrogen into amino acids and protein. And the next slide, Dean, will show us how this is accomplished through Dr. White's work. Next slide, Dean. Thanks. So as we look here, if you can see on there, on the right side, the arrow going into the root, the microbes enter the root and they actually oxidize off, and they'll strip off the cell wall and a lot of the cytoplasm. And those are very high in all the nutrients that the plant needs. So you'll get your nitrogen, you'll get all the spectrum, but it also has all the energy on it, the carbon, the oxygen, the hydrogen. And then as it goes down, the plant will spit in the bottom corner, the little blue slide, probably hard to see because it's small, will spit these bacteria back out into the soil and feed them the sugars, and they can go back out and reacquire more minerals within the soil environment and then go back through the process. So almost like when we're feeding a cow grass and grain and then bringing it in and milking it each day, we're allowing that cow to go out and eat lower quality ingredients to our digestive system, and then giving us a higher, more nutrient dense thing like the milk. This is very similar to how the plant can absorb the biology. So it really is an exciting new discovery that leads us to another way that plants can bring in nutrition. Next slide, Dean. I built this one just to demonstrate a couple different things. When we think about a plant, it takes sunlight with the leaf and it makes water and carbon dioxide into sugar. And when it's digested by the microbes, it re-breaks down into water and carbon dioxide, and the microbes, of course, get that energy, which they need for fuel. Now, I don't want to get too technical into the chemistry, but what happens in this H2CO3 is then converted to this HCO3. That's carbonic acid. And the point of that is, when we want to make a fertilizer, say we're going to make phosphate fertilizers, we take rock phosphate, we add an acid. And this is how nature can do this. If the microbes have lots of sugar, they can actually make this carbonic acid, and when you put it on the rock mineral, it dissolves it and makes it free so that it actually will become plant available. That's another form that the microbes can bring it in. As well, I demonstrated in the bottom how calcium is very important to soil structure. What happens is that the calcium can hold these clay particles apart. Calcium's a lot bigger than the other cations, and that actually creates more pore space. So the calcium can actually, through this chemical means, create a lot more pore space in our soil and allow this water and air to infiltrate that are important to the microbes. Next slide, Dean. So one of the things I think are the biggest fields for agriculture to advance is photosynthetic efficiency. Right now, we're only at about 17% of the photosynthetic. So the plant can actually take a lot more carbon dioxide and convert it into sugars to feed these microbes. And right now, we're not getting that. So I want to talk a little bit more about how we can do this. Now, if we get to say 80% photosynthetic efficiency, that's not going to mean we're going to get 4 times more yield. But what it's going to mean is that a lot of that extra sugar is going to go down into building your soil health. So then we can start looking at how we're building that soil up so that we can get more like that fence line that in the picture earlier. One of the biggest things to this is controlling the flow of nitrogen into the plant. When we put down all of our product, it converts to what is nitrate. And if the plant is pulling in the water and it's full of nitrate, what ends up happening is the plant will try to convert that nitrogen in that form to an amino acid. So it'll start putting its energy on it. And so the nitrogen actually acts like a steroid to the top growth. When we put it on, you'll see the top of the plant really respond and grow. And what's happening is we're actually losing, the plant is using all of its energy up top, and it has nothing left over to feed that herd underneath. And we end up essentially growing a really big top like this Taj Mahal type plant without any strong foundation to hold it up. And this leads to lodging, this leads to, nutrient deficiencies, this leads to the poorer soil structure and a lot of the different difficulties. So I want to talk a bit about how we can manage our nitrogen a little bit better and save on our nitrogen and not lose it, because what will really happen is if you have nitrogen in a low oxygen soil is the microbes will start to consume the oxygen off that nitrate, and it will return to the atmosphere, and we'll lose a lot of that expensive nitrogen. So we can actually add several tons of high quality carbon into our soil, and that's what will feed that herd and build back the soil health. Down at the bottom, I should have threw this equation in before that digestion thing, but really, the whole idea is carbon dioxide and water are converted into these sugars. That sugar is used for ethanol, used for all of our food. When it's decomposed in the ground, that's our gas. So really almost all of our energy came from the sun and the plants converting water and carbon dioxide into energy. So that is the major thing that we're working with. And when I talk photosynthetic efficiencies, I believe we have a capacity with the plant to vastly improve the amount of that's going on in our field, in our crop, and that's where we can actually build our soil as we grow our cash crop. Next, Dean. So what can hinder that process? As I talked about, the excess nitrates moving into the plant. This can cause a loop in which we don't get that exudation. And what will happen is the plant actually becomes very low energy. It doesn't have any energy to feed the roots. And this is why, we're not going to be able to get exudation because there's nothing left. And Converting the nitrate into a protein or an amino acid, it takes a lot of water and a lot of energy of the plant. And when it needs to draw in more water, if it's continually pulling in nitrates, it kind of, like I say, stalls it, and we end up with that effect of a really big top growth, which looks impressive, and we like to see that, but it's not actually, it actually has some negative impacts when we think about how the plant functions and the soil health. Another thing I want to talk about is quorum sensing. I know everyone's probably heard the word quorum. We think of it as a board meeting, right? And you need so many board of director guys there to conduct legal business. And what happens with quorum sensing in the micro world is when you have enough of an organism, they can actually rewrite the plant DNA so that the plant will feed them. When we talk about those particular exudates, if there's enough of that microbe present, it will get the plant to feed it in particular with those sugars. So this is why sometimes in these systems we need to add the microbes just to ensure we have enough present, because most of these microbes just naturally exist in our field, but because there isn't a high enough number, they won't trigger the plant to feed them. Another big one would be a nutrient deficiency if we're short of a particular mineral. This is where sap analysis and different things are important, because we won't get good photosynthesis, say, if we're short of iron. It's critical for the development of chlorophyll. They're finding now as well a lot of the keratin are another molecule that can photosynthesize different waves of light. So we actually can get more photosynthesis if we have abundant iron present within our system. Compacted soils, as we talked about, a lot of these are aerobic microbes. Most of the diseases are anaerobic. And because our soils have been compacted and we have low oxygen, this allows a lot of these diseases to form. But the aerobic guys do need oxygen to breathe and to function. Think about it as if, you have a bag on your head and you can't breathe. You're not too worried about work. You're more worried about being able to breathe. You can't get much done. We need oxygen readily to survive, and the biology is that way as well. So again, that's another consideration. Low carbon. When I use the term carbon, that's the sugars. That's what the microbes can feed on. So we need that as a food source to feed that herd in the soil. So what happens if we get too much nitrogen, too low carbon? So on that fence line stretch, there's lots of carbon, so we have a really nice balance. If we're, say, bacteria thrives best at about 20-to-1 carbon to nitrogen, fungi likes about 30-to-1. A lot of our fields we're getting down below 15-to-1 carbon to nitrogen. And what that means is the microbes will starve in the soil. They don't have food. Now we're trying to trigger this plant, as we said, to feed them, but we sometimes have to kind of prime that pump to get the biology growing so that we can start oxygenating and getting a population there large enough to trigger that quorum sensing and get more microbes and the plant feeding them. Next slide, Dean. Environmental DNA, I just threw this in for interest. When I went through school, we would plate microbes. You swab the root and put it in, or the soil, and you put it on a plate of agar. And whatever grew, we would identify and view it as that's what was there. That was present in the soil. And with the advent of environmental DNA, when they tested soil, they found millions of strands or millions of codes of DNA of species nobody had ever identified before. And this was kind of shocking, because when you put it into perspective, there were more organisms that we weren't aware existed in the soil than every single organism cataloged to that date. And all of these organisms actually require the plant to grow, and they're plant-dependent microbes is what they're called, but they're the ones that aid the plant. And nobody in the soil science field, microbiology, knew they even existed until this recent time. So even now with this massive amount of them, it's a very small percentage. So your people that are most into the field, they only know 2 to 3% of these organisms. There's, 60 to, I think, about phospholubilizers we've identified hundreds of nitrogen fixers. All of these are organisms that the plant would feed if they're present, and we're just discovering them. So it's a really, to me, it's an exciting field because there's a whole lot of new stuff going on. So I'm happy to share it with people, but it's kind of overwhelming in terms of all of the science that's available. Next slide, Dee. So how can we make our fertilizer more efficient? That's one of the things. Okay, we're going to get into that, Brett. Thanks for the question. We'll talk a little bit about it after as well. So salt, as the fertilizer, salt or salinity, I guess, would be one of the questions I have to expand, but we'll talk about that as we go through. So adding micronized carbon helps to bind the fertilizer and the salt a little bit. You might think about humates or heard of humates. One of their functions is to kind of hold the fertilizer to make it more slow release. One of the big benefit of that is that all that nitrate isn't available and the plant can then start to control it. I like the micronized carbons because they're much smaller and they bind the fertilizers and the salts as well, but the food of the carbon itself will help the microbes convert that into bacteria and other organisms in the soil, which then can enter the plant through the rhizophagy cycle, and numerous different microbes like protozoa can consume those, and almost like a cow, their metabolites or manure that comes out is extremely plant available and stimulatory then to that system as well. And also, the next slide, Dean. So some of those strategies for boosting soil health, again, going back to that couch potato scenario, it doesn't happen overnight. We need to think about nutrition, activity, all of these different things about improving our own health, but also with that soil health. We need to think about the effects of the acid and salt of the fertilizer. We need to think about, getting that to start feeding the soil. And why I re-included this picture is as we pump that carbon into the soil, we actually have the potential to start adding the carbon instead of mining it and building back that particular area that's suffering from the drought in this particular shot. So that's where coating that fertilizer, I think, is important with, a microcarbon. The science is showing they're very effective at stabilizing the nitrogen. I think adding the proven microbes will help to make sure we achieve that quorum sensing. Helping, and that's really what this granular inoculant is about. It's that we want to have enough of those microbes that we know can pull phos out of the soil. We know we can break potassium out. We know we can do iron, calcium. And calcium is a dual role. A lot of people don't think about it as an important mineral because it's very abundant in the soil, but it really isn't very available. It gets tied up by a lot of the other nutrients, and it has a critical importance in the soil health, as we've shown how that pushes the plant apart, but also as we bring it into the plant, it gives you a lot of structural strength in that plant, similar to why, we identify calcium in bones and teeth. It gives us a very strong material biologically to do what we need to do. And also with the double cation, it creates like an ionic pump. And they found that can significantly increase its ability to pull in water and nutrients within the plant as well. So another thing we can do is when we start to think about that photosynthetic energy, the more energy the plant has, the more it feeds the roots. Sometimes a foliar spray that actually boosts that process can increase then how much carbon we're putting in to feed the herd back to that scenario. Next slide, Dean. So Dean always tells me, well, what's the simple sort of Cole's notes on how we can do this? And I'm always hesitant to answer that question, because if I say reduce fertilizer by a third, that's a very different thing to a guy putting, say, down 200 actual pound of N, or a guy putting down 60 pounds of actual N, right? So one of the things, just using that as a benchmark, why I would throw that number out there is if we stabilize that nitrogen, there's a lot of science showing only about 30 to 40% of the N we put on is actually ending up in the plant. You know, they use different isotopes so they can track that. A lot of the nitrogen actually burns the organic matter out of the soil, which creates carbon dioxide and releases all the nutrients, which gives a really desirable effect to growing plants until we've burned too much of that carbon out. And when that happens, then we end up in that situation where, you know, we don't have that resiliency. And this is how we can build that back with our cash crop, very similar to how a cover crop would. Now, why I say that is, you know, when we've grown cover crops, a lot of people, we've seen desirable things for them. And as we study what's going on there, we can mimic that with our cash crop if we understand how we can get that process of exudation going and controlling, you know, our inputs. Not that our inputs are bad or anything, but they impact our growing system in specific ways. And we can kind of work with that to make it beneficial to us. So next slide, Dean. Year two, we did quite a few trials with this with FBN down in the States about, you know, fertilizer reduction as we started decreasing, because the soil's kind of like a drug addict, some people compare it to, is we get it on synthetic fertilizer. It needs the synthetic fertilizer because it really just stops feeding the microbes. So they're not there. So we need to sort of, you know, as we decrease the fertilizer, we can build up, and like the couch potato, you can't start out running a mile. You got to kind of work back into that. And the soil's very much the same way. As we move into the second year, we see that we get a lot more biology, a lot more of the carbon starting to form. That allows us some more of that resilience. And by year three, we actually see, as I said before, we've identified over 600 natural N fixers in the soil. As the plant starts to require nitrogen, it's going to start to feed a lot of those N fixers. So we can start to get significant increases in soil carbon. I like to say jokingly, because, you know, if you look at the air, you go online, look up what percent of the air is nitrogen, it's 78%. So we really actually have about 70 million pounds of nitrogen over every acre. And I like to jokingly say it should be harder to sell a farmer synthetic nitrogen than it is, to sell an Inuit snow. And I say that because, you know, there's so much N available, and through this process, we can actually start to fix it. But we really need to, and that's why I like to discuss this, we really need to understand the processes and build that strategy into our system. A lot of agronomists, because they get bonuses for selling for fertilizer, or they haven't gotten into the newer science, don't really portray that to us as growers. So, you know, I believe it's important for us to have an understanding of this so we can kind of look at what strategies work for us. Next slide, Dean. I included this slide. This is actually an older slide. On the right is a canola field. Now, that field we were working on, I believe it was year 4 of a biological program. I don't want to sell this as being this product, because it wasn't, but it was. We were doing a lot of work to build the biology in that program. Beside it, the neighbor wasn't into biology, but he was growing lentils. It was a wet year on heavy clay. As you can see, as you drift away from the property line, it was a disaster. He had sprayed that twice with fungicide, but it, anybody that's experienced this knows it doesn't help at some point. But what really shocked me when I looked at this is you move closer to the biology. It's kind of like one bad apple spoils the bunch, how biology can creep. This is the opposite of that, is the good biology was seemingly moving into this field and giving it protection, because we had really nice lentils. And I would assume that the disease was present there, but obviously something was preventing it from hitting these plants. Now, at the time, I didn't understand a lot of this, but this triggered a lot of my, and the reason I included it is it triggered a lot of my kind of scientific curiosity of what the hell was going on here, that, these lentils seem to be defying this disease parameters that we think about. And that got me into studying a lot more of why would this be happening. And we've since added things like trichoderma that consumes these fungi, but that wasn't part of this. Like I said, this was an older slide. I just, ask questions as a scientist. Why do things happen? These are pretty anecdotal, but, the science is starting to catch up in understanding some of these processes that I was sharing with you are part of how all of this is coming about. But that was my last slide. As Dean had mentioned, we had a little bit of a miscommunication with Mahedra, and he had a more product specific slide getting into the microbes that are actually available in the product, which I apologize, we don't have that, but they're kind of the mycorrhiza fungi, the trichoderma, and then a lot of microbes that are good at solubilizing and promoting plant growth. But back to your salt question, Brett, were you referring to salinity, or were you thinking more about the salts within the fertilizers, or was there a specific thing that you were looking at there, or any other questions in particular?
More of the fertilizer salt that comes with the fertilizer, Dean. Yeah.
Yeah, great. Yeah, great question. Yeah, it is. And that's why, we all know that we can't put down too much fertilizer with the seed, because it burns the biology. And the reality is the microbes are a lot more sensitive than the plant to the salts and to the acid. If you put down high levels of phosphoric acid, for instance, when we think back about those little mycorrhiza filaments, when we do that under a microscope, they just curl up like a hair with a blowtorch. That phosphoric acid will just singe them off. So it's important not to go over too high of a level with the phosphorus. The other side of it is obviously if the plant has a lot of phosphorus, it won't feed the beneficial microbes that can break the phosphorus out. So it's that balancing act. And this is where, I think coating that fertilizer helps make it safe against the salts, but it also allows the plant to be able to access some of the nitrogen or phosphorus without, having enough present that it's damaging the biology. And this is where too we can use it more efficiently. As most people know, most of the phosphorus gets tied up within about 6 weeks of us putting it down. It gets bound into the calcium or the iron, which makes them unavailable and makes our phosphorus unavailable. But the biology can easily pull that back out. But this, by coating the fertilizer with something, when I say coating, it's usually a small amount of like 4 or 5 liters on a ton, but that microcarbon will mitigate the salt and the acidic type potential damages. Go ahead, Dean.
I do have that slide deck that Mahendran had sent me a while ago. So if you happen to have any of those slides you think would be useful for me to present, I'm happy to do that. And if you want to just talk through it, that's fine too.
We can just briefly go through it. It was his slide, and I reviewed it quickly, but I'm really not prepared to present on it. But I do, yeah. If you want to show it, it does show the organisms that are in it. If the group is interested in actually seeing the names, if some of you guys like to go and chase down the scientific studies on it. I think Brett wants to take us to task on some of the science.
Well, there's what it looks
right
like.
Right on. Yeah, so that was the bag we made up last year, just quickly. We didn't have it ready, so but again, they're granules, so it's actually made from distiller grain. I like the distiller grain because the yeast has broken it down, and a lot of the nutrients in there are concentrated. So it's about 3 times more concentrated than the wheat seed because they've pulled the starch out during the ethanol process. And then as well, we have the fiber from the wheat seems to be feeding in our trials the trichoderma. So it actually proliferates as it's coming out of dormancy. All of the microbes in here are in spore form. And this allows them to be very resilient. So this product is actually shelf stable for a couple years. If you leave it in the vehicle and it gets up to 40 degrees, not going to hurt it. If it freezes, not going to hurt it. Until the microbes actually come out of the spore form, which is how they survive for decades in nature, they're actually quite resilient. So.
Can you speak to the types of material?
Yeah, as you go through the slides, yeah, you bet.
Okay.
I think some of the slides actually cover that, so I was just kind of waiting. So these are organisms. You guys might be familiar with Bacillus subtilis. That is the one that's in BASF's pulse inoculant. So they call it dual strain and then charge, instead of that $6 to $10, they charge maybe $18 for it. I don't know what the current prices are, so I apologize. But it's included in this one. Just the cost of it isn't very high. It's good at protecting, solubilizing, and it's a good overall beneficial microbe. And a lot of these are actually the microbes that are known for pulling different things out. This is the quantity in there. And this is sort of when we think about the quorum sensing, is making sure that we have enough present that they can trigger the plant to feed them. So that will be a big thing. And we'll get a little more. I know there's more detail on what each species does as you go through that presentation, Dean. Yeah, so some of those different organisms, like say they can fix nitrogen, some of them solubilize phosphate, some of them mobilize potassium. A lot of people, we're kind of given this perception, well, if we're mining this material, are we not going to run out over time? But there's actually enough for thousands of years. It would be more like going in with a pail and scooping, trying to empty your lake or something. It's not going to happen nearly as quick as we've been led to believe. I think there's literally thousands of years. If you're in Saskatchewan, potassium is typically extremely high. The difficulty is only 1% to 3% of phos or potassium tends to be available. But the biology, these microbes with those exudates are the way to make it available. So. And like I say, there's lots of different solubilizers for micronutrients. If you're running into difficulties with iron or copper or zinc, those types of organisms, those minerals will become much more available as well. This is just some of the pictures of how, the different microbes form around the roots. And we talked about in my slide how mycorrhiza will go into the roots. One of the ones we're really excited about is trichoderma. When growers in the hort industry aren't allowed to use fungicide, they use trichoderma, but it's very expensive. And what trichoderma is known to do, it's a fungus, but it consumes pathogenic funguses. So it has been shown to have great effect on fusarium and a lot of these other diseases. in plants. We're still kind of early on in applying this. We do have some third-party trials going with things like actinomyces and other disease conditions to see if we can actually eat those microbes. And you know, if we say group here lentils on infected land or even clubroot, what is the impact this these protective and actually funguses that can consume those diseases might have?
So you said you've got some trialing this year on, we'll call it the lentil zone that can't be the lentil zone. For some guys that have excess disease, we're going to have some outcomes this year on how this product works in that situation. Is that correct?
Yeah, we're doing some third-party research with facilities that are doing testing, and they have contaminated land, so they're going to do plots of lentils on the contaminated land.
That's really cool. Yeah, game changer stuff. Okay.
We're hoping so.
Yeah.
No,
Yeah.
no,
Oh, potential, right?
don't want to sell you as it's a fungicide until we get some infield
Understood.
data, but so yeah, the big thing about it is designed to increase the availability of a lot of these nutrients. They're there in the soil, but we've kind of, through how we're farming, we're kind of getting to where the soil's like a medium, and it's almost like hydroponics where we're trying to feed it all of the nutrients. And like I said, the nitrogen tends to break down the carbon, which releases a lot of nutrients, and it works great when we have lots of carbon in the soil or lots of organic matter. But as that organic matter depletes, and I think, you know, I worked with quite a few guys that were growing corn, and of course they're pounding down huge amounts of nitrogen, and a lot of them started to lose you know, yield, and they weren't getting the response from the nitrogen. So we started to work with them on how, you know, we can sort of kind of start rebuilding that carbon and bring that land back into being more productive, because some of it really started to kind of fall off a cliff at the end of the day. And as fertilizer gets more expensive, and you know, and our, as I heard a little at the start, commodity price is a little shaky at the moment and lower than we certainly need. We need to make sure we're getting the most out of our nutrients.
Brett had one question about where sulfur might fit into any of this discussion.
That's a great question. I find that the ones that are often missing because they're very mobile in the soil are sulfur and boron. And typically sulfur is very important for 3 of the amino acids. So it is good to have some sulfur within that mix. This will definitely help if you have elemental type sulfurs. I don't want to sell anybody's brands, you know, the Tiger 90 or you know what I mean, the elemental sulfurs. This will help make them available. Because of that, those acids will definitely help break them out. Otherwise, you know, ammonia sulfate is a really strong salt. So I do recommend, you know, when you're putting down your sulfur to potentially look at coating. Don't get too, a lot of the soil health guys will use what's called thiosulfate, which is a little less, antagonistic to the biology. But like I say, I find just coating it and not getting carried away with how much we put down is important. But keep in mind that sulfur is one of the ones that can be short in our soils. I know there's pockets where copper can be short too. Things like iron and calcium usually are not short. They're 2 of the 5 things that make up the soil. The big 5, of course, are silica, oxygen, aluminum, which is very present but tied up so it doesn't come out, and then calcium and iron are very prevalent in our soils. Yeah, these were just a couple of the different just plot trials Mahidran and I were doing just to kind of get some feedback. but just showing we had some stimulation. This was actually done on a field that had some biology within it. Like we knew it had decent soil health. We did spark about, I think, a 24% bigger roots and about 20% bigger tops at the time we dug those samples. So. Yeah, so this just talking about the rate. What we were looking at was 2 pounds to treat an acre. It's a granular inoculant. So essentially we want to put it down in the seed row so that the microbes are as close to the seed basically as possible. But working similar to how, you know, you would apply granular pulse inoculants through the tank that way. And we were looking at if guys were interested, as Dean was talking about, doing 80 acres, that we would provide them with that product. Again, we want to kind of start to learn. I know it's really late to the game, so I don't want to put pressure on anybody, because if we do kind of have high fertilizer rates, it tends to, if the plant doesn't need nitrogen, it's like we know with rhizobium, if you put down, say, 100 pounds of actual N on peas or lentils, the rhizobium won't fix any nitrogen just because plant doesn't need it. It won't put its energy into it. Yeah, so I think that was the main part of it. There's also some of those growth stimulants in there. As you guys may be aware, they like the gibberellic acid. Some of these microbes produce compounds that stimulate root and plant growth. And that's why, you know, they're long established. All the organisms in here, nobody's really done a good job of mycorrhizal fungi because you have to grow it on a plant. And Mahedrin actually came up with a patented way to grow a lot of the plant roots and grow a ready supply. There's actually 6 different strains we have registered with the CFIA now and with globally that we've identified that are beneficial within the cereal crops. One thing I would caution with mycorrhizal fungi, it doesn't form a relationship with brassica plants, which is, of course, canola falls into that family. There is recent research, though, that shows that trichoderma bridges that relationship. So we're following that. We don't have a lot of data to support that yet, but the science is showing that when you combine trichoderma and mycorrhizal fungi, that canola can certainly pull nutrients out of the mycorrhiza network. To me, though, that would say if you just put it down in the canola crop, it's going to be a limited benefit. But if you have it in the previous crops and you build that mycorrhiza network up, it may be significantly. They've shown canola can draw energy from it. It just doesn't feed it, so it's not as powerful an organism in the canola crops.
Excellent. Well, that takes us to about an hour to that. We're just at the 9:30. So I want to thank you, Dean, for the presentation part. What we'll do is we'll hang around. Or Dean, are you able to hang around if we have some questions?
Yeah, sure. Yeah. And
Yeah, so,
you know, I just scratched the surface on most of these topics. I hate getting too sciencey because, you know, it can turn people off. But there's a lot of science emerging, and you know, I always look at it as, you know, how can we use this in the farm situation to benefit us? And I know Carol's on the call, and we're, you know, we've been looking at how do we reduce the fertilizer rate so guys aren't spending more on the input bill, still get as good or better yields, and then start bringing in some of these soil health benefits. And I know Carol has been working on programs that would help give revenue and yield type insurance that, you know, if you're looking at doing it, it gives you that added layer of security with your farm in case things go sideways.
yeah. Excellent. Yeah, we'll be having Carol on shortly, like in the next week or two, just depending on how everything comes together. And we've got there's some exciting developments that he's been pioneering, and that I didn't know, Carol, if you had anything briefly at all. Don't want to put you on the spot, but if you'll have any asides from this presentation.
No, I really enjoyed that. Thank you, Dean. Yes, I'll be able to present with you, Dean, in future what insurance options are available so that farmers can take advantage of a risk management that work in favor for each farmer.
Yeah, and I think we talked a little bit about our goals, and that is to be able to not increase the farmer's costs between these different biological practices, adding them into what we're doing, and still be able to get the insurance premium in there without, you know, being a cost increase to growers. And that would really be, I think, a beneficial program.
Yeah.
Yeah, there's some pretty cool modeling we'll be sharing. It's just kind of all getting
Yeah, my
right now.
targets are more for next season, just in case people are wondering about this year. You know, everybody's probably made a lot of your input decisions, or I don't know where people are at, but yes, definitely we're still working hard towards those models and doing more and more data, and excited that option's available, because I know as a company, is if you tell people to reduce fertilizer and it doesn't work out, there's a lot of legal issues to that. So the insurance side of it for grower, for even manufacturers, is really I think a big advancement in what we're trying to do.
Yeah, thanks for that, Dean. So what I would like to briefly touch on is what we need, what you're looking for today, Dean, and that if you've got about, what is there, like 1,000 acres left of trialing you would like to fill in?
Yeah,
so
we were, well, we
in
could make about an extra 1,000 acres, just so if guys were interested, wanted to try it, wanted to be a part of it. I really like it for dry areas if you're going into a drought and you didn't want to throw all your money into your fertilizer, because there's a lot of things within this, if you do get the rain, that can help you get the nutrients out. And like I say, with sap analysis, if we went in and found, oh, well, maybe we're short of N, P, or K, or one of those nutrients, we can still, foliar apply that and take benefit with our rainfall without, spending all those nutrients up front.
Yeah, so just from a practical perspective, those farmers that have that inoculant tank, that extra tank, this works well to apply in there. It's only a 2-pound level, so ideally it goes directly with the seed and that. And go ahead, Brett.
Sorry, I was not trying to get an urgent question in there, but I just wanted to ask, the foliar one, Dean, does that actually go in the plant, or does it go through the surface roots when it gets rained in, kind of thing?
So good question. There's kind of two different products. A lot of guys are putting down a carbon source or different stimulant with the burn off, and that one definitely goes down and kind of starts feeding the biology, the microbes, getting them going, and that would feed through the roots. And then when we look at foliar sprays, we would be designing those ones to go in through the leaf and stimulate through the leaf. That it would be a very different sort of product. Some of them, if they're carbon and aminos and things like that, will work in either scenario. They're pretty universal that way. They're going to be a food source for wherever they kind of first, whatever gets a hold of them first is going to use them as a food source. So there would be potentially, if you went out and said, did a sap analysis, you'd probably look at whatever minerals are short, adding them with the energy sort of foliar, which will help it enter the plant and make it safer. Some of these, especially zinc, copper, iron, can really burn a plant. And having them bound with the carbon makes it way safer. And the other part of that then is you're actually adding energy to that plant at the same time. And what I found is if you are into a refractometer, it's kind of the simplest tool, but to look at the bricks, and certainly when I've used, say, with glufosinate on Liberty tolerant canolas, if we go out 6 days after we spray and we add one of these photosynthetic enhancers, we'll see way more sugars. Like usually it'll be 4 to 5 on a control, and we'll see, double digits bricks on the sprayed part. And really what that is a lot of sugar. And if you've got good biology down below, it's going to pump it to those guys down below and trigger them. If you don't have biology down below, it actually just essentially does very little, because the plant won't have anything to do with all that sugar. It may just downregulate it. So and that becomes the strategy then too, of how we stack these together to get the maximum benefit from them. But also there's a lot of synergies if we kind of understand that energy and trying to increase that photosynthetic energy of the plant to feed those microbes.
Very cool. Very cool. Yeah, thanks.
You're welcome. Good question.
Yeah, so relating to the ideal candidate, if you want to trial it, along with there's the application method, and the second thing would be you would want to have a zone where it's deficient, known for fertilizer levels and that, just to make sure the product can do its thing, type of a thing. Hey, Ryan.
Hey, Dean. I was kind of in and out of the meeting. I maybe missed this. Maybe it was already spoken about. The granular product. Have you done anything to make it more flowable? Because the little trial pack we tried last year, it was just sticky. Didn't want to flow.
One of the big things, yeah, we added a new what would you call it, sealer. It's actually made from kelp, so it brings nutrients in. One of the big things too is if it gets warm, we just find it's good to kind of throw the bag on the ground a couple times to smash it up. And also the other thing is, last year we just kind of roguely took balls. We've sized them now, so they're all like the size of a urea prill. And so hopefully, and that's great feedback, because we kind of mostly just wanted to get them out there last year to see how they flowed through the equipment. So.
Yeah, excellent. No, that's good. I've got a few questions. I'll just ask, does anybody else have other questions? Otherwise, I've got a few things in my head.
I was just going to say, Dean, Three Hills guy there, he might have some dry areas in the special areas east of him there, east of him there. So okay. You can check with Henri to see if there's some acres there you could get onto.
Yeah, and we do intend to try to work a little towards getting some agronomists set up to be kind of help with prescription agronomy as we, talk about sap analysis. There's a lot of great scientific tools to kind of aid us in going about this. I don't really have time to do the agronomy role, unfortunately, but I think as we develop, we'll certainly look to do that and help guys, especially in crop and with their soil tests, to just different advisory on that point.
Yeah, cool. One question I had was you're using one of the biologicals is similar to the starter inoculant. I don't remember the company, but I don't remember the company. But for using for pulses as an inoculant, have you done any trialing of just using your product as an inoculant versus the extra stuff out there?
Good question. So there are microbes within our granule that make it, they don't play nice with rhizobium. Now you can still use rhizobium, but it needs to be in a separate granule or a different application method. What we intend to do, we actually have registered rhizobium. We'll make the same granule and then probably just pre-blend it for the grower for pulses.
Okay. Cool.
Because the rhizobium is definitely beneficial. The one that breaks out the phosphorus in like the tag team of the past. That one is actually within this as well. So that's one of the phos solubilizers that are present.
Mhm. Something you touched on at the beginning was we had the water sitting on top of the soil, and there's various places in a lot of fields where it does that. And so what have you determined could be the minimum soil compaction level, and what tool would you use to see where your soil is at, just to benchmark it, just to see where people are at?
Well, that's a great question. Like the sort of old school standard is the penetrometer. If you take a penetrometer out and you're over 300 psi, you're not going to get any air into that soil. If you get down to under 200, sort of that ideal zone, sort of 150 to 200, you're going to get good structure, good airflow. So that is an excellent mechanism to, I guess, quickly determine how compacted your soil is. Also, how deep we can have in, your aerobic zone. It will expand as we continue, but a lot of times you hit a hard pan, and that's probably as deep as your feeder roots can acquire oxygen and grow and be functionable. So yeah, great question. Also, the EC meter, kind of applies to salt. They're actually finding that microbes have a charge. And if you don't have a lot of salts present, you can sort of see how much microbes are available within your soil using an EC meter. I like it, but it's got a lot of sort of nuances to it. One, that the salt will give a false reading. B is the soil texture. You have to kind of modulate your reading by a soil texture. And C, the moisture in the soil helps conduct a charge, so that can be an important one too.
Is that like that EM38? Can you get info from that too, that they're using, the SWAT map guys and that thing?
We're working on that. Honest answer is I haven't done enough work to be able to give you sort of a scale on that as to what numbers are ideal. It wouldn't take long though, as you go into a healthy crop and you can track those numbers. We could probably build something. I just haven't used the technology enough to give you an answer on that.
In your spare time, hey?
Yeah. No, we'll start looking into it. Yeah.
Cool.
The more we can learn from the technologies we're already learning, that's the ideal. Yeah.
Just like we have the soil testing for the NPKS and all the rest of it, it'd be cool to have the biological benchmarking done as well, just to see what's cooking or not.
Yeah, anybody that's heard of the Haney test, that's actually how it was developed. Some of the guys that were using a lot of cover crops were showing very low nitrate level, not applying nitrate, but growing really good crops. And some of the scientists finally broke down and determined that, well, all that nitrogen's in the organic matter, and it's just not showing up on a nitrate test. So they added 7 or 8 different tests to sort of break out all this extra nitrogen. Turned out there was actually 300 pounds of available nitrogen on that land. So adding nitrogen was a waste of your money.
That's what that gal that's working with Continuum is touting, I think, Dean. Is that right?
Yeah. Yeah, I know there's a lot of the soil health labs are developing different protocols. Haney's one of them, but there's other ones that do kind of give you a better picture. Now, I would caution guys, if you haven't been going with the soil health, probably the extra dollars for those tests aren't very useful to you. But as you sort of start going into and doing that, a lot of your nutrients can be contained within the organic profile, and they're not going to show up as nitrates or ammonias or phosphates or what would show up on a standard, a historically standard fertilizer test.
Something else that came to mind as we're talking about this, and it's been brought up to me before, but what factors are contributing to the rapid development of kochia patches and stuff relating to your appropriate nutrient balance, healthy microbes, and all the rest of it? Like something we chatted about yesterday is what is the plant telling us when something like that is going to grow, but it sure as hell ain't going to grow wheat or something else properly? Like what?
I got to put my hippie hat on and say that, you know, what are the weeds telling us? I've been looking at, I've actually been reading different books on that, and it's amazing that, you know, if we look at the weeds we have and we test those weeds and see what they're high in, they'll often tell us what minerals deficient because they have a competitive advantage growing with that. And I think it's actually nature's way of pulling that nutrient and making it available for the crop down the road, right? Kochia has an amazing ability to draw in water in very dry and salty conditions. That's why you often see it down in the saline areas. So it's very competitive in that sense. But it also is good at growing in compacted soils. So it is one of the ones that likes compaction. And it also grows in soils that would be lower in fungus. So as we build up that biology and get a better carbon to nitrogen ratio, things like kochia, cleavers, and wild oats all vastly prefer bacterial soils. And our nitrogen stimulates bacteria, as we talked about. It kind of, with the organic matter, it will create a bacterial soil, and the funguses won't prevail. So a lot of the weeds tend to be part of being a bacterial soil or a compacted soil. You know, things like Canada thistle, quackgrass, dandelion, they have an incredible ability to pound through very compacted soils.
Mm-hmm. Thanks for that. Yeah, in the last 3 weeks, we had a very high-end agronomist on and relating to the ag chem options for control of kochia, and we've really exhausted a lot of that stuff, and we've painted ourselves into some corners, and we need to look at a holistic approach. Yep. Versus you know, the one line of thinking.
You know, that triggers something. I met with a lady, Nicole Master. She's actually that slide that I gave you with that rhizo sheath. She was the agronomist that did that. She's since moved to Montana, and she has lots of farmers with 30,000 plus acres. Very, very bright woman. I think one of the top 10 soil health people on the planet, without a doubt, in terms of actually being out on farms and making a difference. But one of the things that she noticed, and I started to chat with her, is that a lot of plants build resistance through what is called the shikimate pathway. And when we're building the carbon back up, it seems to reset the pathway, and we're getting much better herbicide performance. Like these ones that we had resistance weeds to are starting to work like they did when we first used them. I'm not going to say I have all the answers to that. We started to look at it when we added a bunch of those guys with our FBN team on the science side, because that was something I was intrigued with, because we had a lot of generic, obviously, technologies, but, you know, it seemed like things like glyphosate killed kochia a lot better once upon a time, you know, and a lot of these other plants are getting resistant. So for some reason, that one really triggered me, because obviously I had a company at one time that sold generic herbicides. Plus, I'm interested on the soil health side and these different products. But a lot of these, you know, they found different grasses and stuff too were dying at much lower rates of glyphosate. And one of the things, that other picture I showed at the end with the wild mustard in the lentils, The
Mhm.
guys who were using our biostimulant type products were getting much better control of the wild mustard in the lentils. Now that might be because the crop is simply competing and not dying, but it is, those things are expensive to study though. So like I say, I think though, you know, a lot of, like you say, this integrated management will have different layers of benefit on that. Just to have an exact answer on a lot of it is difficult.
No, that's cool. Great. Well, we've went that extra half an hour with our beyond the normal time, where lots of very cool things get brought up. And I thank you very much, Dean, for this, and thanks, Carol, for sitting in and getting your take on a couple things. And we look forward to the opportunity when we have you. And does anybody else have anything that's they're wondering about before we call it a day? Fantastic. Well, thanks very much. Appreciate each of you guys, and I hope the weather cooperates. We'll see what happens. Saskatoon, it's clearish yet, so we'll see what happens over this 10 to 20 centimeter snow they're threatening.
Yeah, we were white this morning and it's still snowing. So if
Yeah.
it's coming from the west, it's coming.
Yeah, exactly.
It hasn't
Right on,
petered
guys.
out yet, let's say. How about you,
Yeah.
Greg? Are you getting it down there? Down in the
No,
desert?
a couple spits, that's it.
Oh, okay.